Hello, I'm Li Wu from TU Delft. Today I will be presenting our work characterization and fault modeling of intermediate state defects in STT-MRAM. Intermediate state defects are a unique type of STT-MRAM device defects. We identify these defects on STT-MRAM wafers based on silicon measurement. This work is a collaboration between TU Delft, Cognitive IC, and IMEC. STT-MRAM is gradually entering into commercialization. There are a lot of startups in the world. For example, Fspin is a pioneer in this field. You cannot actually buy STT-MRAM chips from this company. And pretty much all big foundries in the world are also heavily investing on this technology, especially for embedded applications. And just like all semiconductor products, to enable mass production, we need high quality and cost-efficient test solutions. But STT-MRAM is new memory technology. It has new failure mechanisms. Some of them are not well understood yet, and there is also a lack of silicon data in the community. On the right side, you can see a team image of STT-MRAM cells. So the bottom part and top part are no different from the conventional CMOS process, but the middle one is STT-MRAM device, which is like a plug-in component between two metal layers. And it has been demonstrated that MTJ internal defects cannot be modeled as linear resistors, for example, pinhole defects and ceph defects. As an alternative, we propose device-aware tests to specifically address device internal defects. In this work, we identify and characterize a new type of MTJ internal defects, which we name as intermediate state defects. We develop an accurate defect model. And we also demonstrate incapability of conventional test approach. And using our own defect model, we can obtain accurate and realistic fault models for test development. Next, I will first briefly introduce STT-MRAM fundamentals. Then I will present some measurement data about intermediate state defects. Then I will show you device-aware defect modeling and device-aware fault modeling. In the end, I will draw some conclusions and talk a little bit about future work. The data storing element in STT-MRAM is called magnetic external junction. It has three basic layers. If the magnetization in the free layer is parallel to the magnetization in the pin layer, the device is in P state, which has low resistance. If they are in anti-parallel states, the device shows high resistance. There are a lot of technology parameters for MTJ, for example, the cross-sectional area, TMR, and HK. 1T1 MTJ is the most basic cell structure. It consists of an MTJ and the NMOS as selector. You can do read and write operations by applying a current with certain direction and magnitude. And three key electrical parameters: resistance, critical switching current, and the average switching time. Let me first explain our experimental setup to test P to AP switching. On the right side, you see the pulse configuration in each cycle. First, we apply a negative pulse to initialize the device to P state. Then we apply a small but long pulse to read back the resistance state. And then we apply a positive pulse to test P to AP switching. Again, we need to apply a small rate pulse to read back the resistance. And we have repeated this process 10k cycles. Here you see the measurement results. For the majority of devices being tested, we only saw two states, AP state and P state. However, for a small fraction of devices, we saw a third state. And we observed that the resistance of this third state is always between RP and RAP. This is why we name it as intermediate states. Another key observation is that the occurrence of intermediate states is always probabilistic, which means that it occurs only in some cycles, not all measured cycles. So what does the occurrence probability of intermediate state depends on? Well, we did a lot of characterization on our devices with different sizes, and we found it depends on a couple of factors. First, bias voltage. In this figure, P sub ST means successful transition probability, and P sub IM means occurrence probability of IM states. And you can see as the voltage increases, the intermediate states, so this orange curve, it increases in the beginning, and after reaching a peak, it goes down. And this is a general rule for all defective devices. So two key observations. First, these orange curves always exhibit a Gaussian function. Second, the peak always maximizes at the voltage where the successful transition probability is around 50%. So you can see these gray squares on the green curves. And we also found device size plays a critical role. So in this figure, you can see the larger the device size, the more vulnerable to IM state defects. Next, I will show you how we model this defect using device-aware defect modeling approach. Basically, the key idea of device-aware defect modeling is to first identify which technology parameters that are influenced by a defect. Then we can incorporate the effects of the defects into these technology parameters. And thereafter, we can map these technology parameters into electrical parameters. This is a key difference from the conventional defect modeling approach. Conventionally, any defect inside an MTJ is modeled as a linear resistor, either in parallel to the device or in series with the device. And based on our measurement, analysis, and literature study, we think intermediate state is mainly caused by partial switching of the free layer. For example, in a P to AP switching, some parts switch to the intended direction, but some parts remain in their initial direction. Therefore, we can model intermediate states by splitting the entire free layer into two subregions, P region and AP region. Here, we need to introduce a key defect parameter, A sub IMP, meaning the normalized area in P state with respect to the entire cross-sectional area. So here, I will skip all the modeling details. If you are interested, you can read our paper. Since we have collected silicon data, we can do fitting to optimize our defect model. By fitting to the measured RV loop, we can extract RP and RAP at a given voltage. For example, in our rate operations, the rate voltage is 10 millivolts. Then we can extract RP and RAP and feed them into our defect model. In this way, we can calculate the resistance in IM state at a given value of the defect parameter A sub IMP. We also did fitting to the measured occurrence probability of IM states, and you can see our simulation results match the silicon data very well. Once we get a good defect model, we can then do device-aware fault modeling. We simulated a 3x3 STT-MRAM array based on realistic STT-MRAM designs. We injected an IM state defect into the central cell C4. All neighboring cells are defect-free. And we simulated all these operations. And this is our fault analysis procedure, which is very systematic to validate all possible faults in a predefined fault space. We observed two memory faults in our simulations. They are intermittent write transition faults, up transition and down transition. And you can see our fault modeling results are very consistent with the silicon data. We also compared our fault modeling results to the results using conventional resistive model. Our device-aware approach gives us two hard-to-detect faults. However, the conventional approach led to 4 easy-to-detect faults. And you can see there is no overlap between these two circles, which means that our approach can give us unique and realistic faults, which accurately represent intermediate state defects, and this can be in turn used to develop high-quality test solutions. And in contrast, the conventional approach led to wrong sensitized faults, leading to test escape. In other words, if you are going to develop a test to cover all these faults, you will not be able to detect intermediate state defects. This contour plot shows the distribution of intermediate state with respect to write time and write voltage. This red zoom is actually a hotspot for intermediate states. The bottom left corner and top right corner have little intermediate states. If your operating points end up in this corner, you will have permanent write transition fault because your write energy is too small. This fault is very easy to detect using March test. If you want to get rid of intermediate states, you can put your operating point in the top right corner. using large write voltage and time. But this is also very costly because you will have a large power consumption, long write latency, and short lifetime of endurance. You can also move the operating point to the middle area. Then this means moderate write voltage and time. And now you can see the cones on the right side becomes pros on the left side. But in this case, we need to come up with a test solution to read out memory cells with intermediate states. Another solution is that you can use strong ECC to tolerate memory faults caused by intermediate states. You can also take a look at designs from Intel and TMC. Basically, they all use moderate write voltage and time. To sum up, intermediate state defects can be design issue or test issue depending on your specific design and operating point. So these two aspects are actually an important trade-off. Let me conclude my presentation. First, there are known unknowns. STT-MRAM has unique failure mechanisms. Some of them are not well understood yet. For example, intermediate state defects, which is the topic of this work. Second, the conventional test approach is deficient for STT-MRAM. This is because linear resistors are not qualified to model MTJ internal defects. They may sensitize unrealistic faults, leading to a waste of test time and resources. They result in low-quality test solutions. As an alternative in this work, we apply device real test to intermediate states. We have seen that intermediate state occurs depending on bias voltage, device size, and the switching direction. They lead to intermittent write transition faults. And clearly, intermediate state defects require dedicated DFT designs. Currently, we are working on DFT for the detection of intermediate state defects. Basically, the idea is we need to first sensitize intermediate state. Then this can be achieved by using weak write operations. This work will be published soon. Okay, that's all I've got. Thank you for your attention. If you have any questions, please feel free to ask me in the Q&A session. If you are watching this video after the live session, you can also send me an email.